What if changing just one ID in a URL let you clone confidential documents that were never meant for you to see? And what if you could go even deeper, exploiting a hidden email template engine to quietly read files straight off the server just by tweaking your username? I'm Amin Malikpour and you are listening to Hacked and Secured Pentest Exploits and Mitigations. Today, we are breaking down two real-world exploits that required no special tools. First, an IDOR vulnerability that let attackers steal private files using nothing but a predictable ID. Then, a clever SSTI that leaked backend files through a password reset email without ever touching the front end. And before we dive in, if you have come across something interesting in your own pen test, send it in. We are always looking to feature interesting findings from the community. No need to write a full story. Just drop the details and remember to keep client info private. You will find the Google form link in the description. You upload a file, maybe it's a medical report, a contract, something personal. You hit submit and you think, alright, that's secure. Only the right people can access it. But what if I told you someone else could download the same file? No hacking tools, no brute force, just by guessing an ID. Crazy, right? That's exactly what Oxley's uncovered in a report on HackerOne. An insecure direct object reference or IDOR that allowed attackers to clone and access private files they were never supposed to see. Before we get into the attack, let's quickly break down what IDOR is for anyone who's not familiar with it. Imagine you are staying at a hotel. You have been given room 305, and your keycard is supposed to open only that room. Now let's say the hotel made a big mistake. They never actually check whether your keycard matches the room you are trying to open. They just assume you will only try your own door. But out of curiosity, you walked up to room 306, tried the same keycard and it opens. You tried 307, same thing, it opens. No one's checking if you are actually allowed in those rooms. That's basically what an insecure direct object reference or IDOR looks like. The app gives you access to something like a document, invoice or attachment using predictable ID in the URL like /attachment /123. But it doesn't really check if that ID belongs to you. It just blindly trusts that if you know the number, you are authorized. So what happens if you change 123 in that URL to 124? In a vulnerable system, it might just hand over someone else's file, no questions asked. Alright, let's get back to the story. Oxley's was testing a secure online portal, the kind that handles sensitive documents, medical records, legal files, the kind of data you don't want falling into the wrong hands. While poking around, they noticed something odd. The file IDs looked a little too predictable. doc102, doc103, doc104, that kind of pattern. Simple, sequential, no randomness. Then while digging through the network traffic, they spotted something even more interesting. An internal API, a hidden endpoint that let user clone files. Here's how that API worked. You would give it a file ID and it would make a copy of that file and attach it to your own profile. The problem? It didn't check ownership. It didn't ask, are you allowed to access this file? Or is this file even yours? It was vulnerable to insecure direct object reference. It just quietly responded, file cloned, here you go. No alerts, no logs, no questions asked. Now put yourself in Oxley's shoes. You have found an internal API that lets you clone any attachment in the system. No checks, no restriction. What would you do next? Start testing file IDs tied to high-value profile and scrap whatever attachments you can find. Look for internal documents or reports that might help you pivot deeper into the system, or just automate the whole thing, clone hundreds of files in a minute. This wasn't a minor bug. This was unauthorized access to sensitive data at a scale. So here's what Oxley's did. They crafted a request using the cloning API, basically telling the system, hey, take this random file ID, say doc104, and just copy it to my account. And the system replied, sure, give me a second. And just like that, it worked. Once the file was cloned and linked to their profile, they could easily download it like they owned it. And we are not just talking about profile pictures. Some of these were deeply private documents, including personal medical records and even classified reports. Here's the full attack chain step by step. First, predict or enumerate valid file IDs. Then use the internal clone API to copy the files to your own account. Finally, download it through the normal user-facing endpoint. No error, no alerts, just access. You would think apps wouldn't still fail like this in 2025, right? But they do. In real-world pentest, IDORs pop up all the time. Why? Because systems are often built on assumptions like, no one's going to guess these IDs, but they do. Internal APIs aren't exposed, but they usually are. Front-end checks are enough. Believe me, they never are. And the trickiest part, these flaws don't hide in fancy features. They show up in everyday stuff like file cloning, shared links, or document previews. Places where access checks quietly get skipped. No fancy exploit needed here. Just changing a number and walking right in. So, what was the root of the problem here? Simple. The system made a few critical assumptions. It exposed a backend cloning feature without properly securing it. It didn't check whether the user actually owned the file before cloning it. And once the file was cloned, it just assumed, well, now it's safe to serve to this new user. Here's how this could have been prevented. Always validate ownership. Whether it's cloning, downloading, or sharing, check if the user has the right permission. Treat internal APIs like public ones. Just because they are not exposed in the UI doesn't mean attackers won't find them. Block access based on IDs unless the user is explicitly linked to that resource. And finally, avoid using predictable IDs. Use random, unguessable identifiers instead. This vulnerability didn't require advanced skills to exploit. It just took someone looking in a place no one else bothered to check. Alright, fellow pentesters, here's how you find vulnerabilities like this in your daily engagements. When you see predictable IDs, things like attachment IDs, document numbers, or user IDs, don't just observe them, start modifying them. Try values just before and after the ones you have been assigned. Look for patterns, see how far you can go. Test every API endpoint you can find, even the weird ones buried in network traffic. Just because it's undocumented doesn't mean it's protected. Some of the best IDORs hide in places developers assume are safe. And finally, use tools or scripts to enumerate object IDs at a scale. If the format is consistent, automation can help you quickly identify what's exposed. Security isn't just about locking things down. It's about thinking through how system behaves when users or attackers don't follow the happy path. Because sometimes the most dangerous breaches start with the most innocent-looking request. And in this case, all it took was an ID, a broken controller, and a platform that trusted too easy. That's the kind of oversight that leads to full-scale data exposure. We started with a stored file being cloned and exfiltrated through a broken object reference. Then we saw how a predictable attachment ID led to full document access. But what if I told you the next attack didn't even need predictable URLs or broken logic? No need to brute force anything. No need to escalate privileges. Just one special payload inserted into your name that quietly pulls files from the backend server. This is exactly what R29K reported on Bugcrowd, a server-side template injection or SSTI that gave attackers access to local files on the system. Before we get into the attack, let's take a second to break down what SSTI is. SSTI stands for server-side template injection, happens when user input is passed directly into a backend template engine without proper sanitization. Instead of treating that input as plain text, the engine interprets it as code. This lets attackers inject expressions that get executed on the server, starting with the small things like mass operations, but potentially leading to serious issues like leaking sensitive data or even executing system commands. Think of it like this. You are at a bakery that uses a system to print custom messages on cakes. You write happy birthday and they print it, no problem. But what if someone writes delete all orders and the bakery system actually runs it instead of just printing it and actually deleting all orders? That's SSTI. The system tries to input too much and instead of just displaying it, it executes it. Alright, let's get back to the story. R29K was testing a small web app, nothing fancy. Most obvious bugs were patched. Then he noticed something interesting. The edit profile page allowed the special characters in the name field. That's always worth testing. So he tried something simple and changed his name to 2 opening curly brackets, 7 multiply 7 in quotes, 2 closing curly brackets, then a space and the word test and saved it. Let me repeat the payload one more time. 2 opening curly brackets, 7 multiply 7 in quotes, 2 closing curly brackets, then a space and the word test. So here's where it gets interesting. After changing his profile name, he expected to see something like 49 test show up somewhere on the site. Maybe in the account setting, maybe in the header. But it didn't appear anywhere. No reflection on the front end. No visible output. It looked like a dead end. Maybe this app was not vulnerable to SSTI, but instead of dropping the test, he thought like an attacker. Where else could my name show up that I'm not seeing it directly in the browser? And that's when it hit him. Emails, specifically the password reset email. He headed over to the forgot password page and submitted a password reset request for his account. A few seconds later, the reset email landed in his inbox. And right there in the greeting, Hello 49 was the proof of SSTI. The payload has executed. The mass operation inside the double curly brackets ran on the server and the output 49 was now embedded in the email. That's when it all clicked. He had found the server-side template injection vulnerability executing inside the backend email system. Once he confirmed the payload executed, it was time to move from discovery to exploitation. But here's the thing. Just knowing that the system is vulnerable to SSTI isn't enough. To go further, you need to know what template engine is running on the backend. Because every engine has its own syntax and knowing the template engine defines what you can do and what payloads will work. So he kicked off the exploitation phase by throwing in a few test payloads. First, he tried a common test in some template engines to try and run shell commands by treating system as a filter. But in this case, the email came back blank, no output at all. Then he tried another payload used in template engines that expose file reading functions designed to extract 30 characters from a specific file on the server. Same result, blank email. He tried variations, different functions, different formats, and every time either the server silently stripped the payload or returned an empty string in the email body. This told him something important. Either the template engine was sandboxed, meaning dangerous functions were disabled, or the app was silently filtering out certain type of payloads behind the scene. But he didn't stop, and instead of guessing blindly, he did the smart thing. He backed off and started fingerprinting the engine. He looked at the syntax of the earlier payload, the one that worked and returned Hello 49 in the password reset email. The format, especially the use of single quotes inside the double curly brackets, looked a lot like Twig, which is a popular template engine used in a lot of PHP-based web apps. So he started digging into Twig's documentation line by line, looking for exposed functions that could be abused without needing system filters or direct command execution. And that's when he found source function. This function in Twig is used to include the contents of a template file, and in some configuration, it lets you pass a file path directly. So he crafted a new payload using double curly brackets, wrapping a source function that tries to read the /etc/hosts file. Then once again, he triggered the password reset. And this time the email didn't come back empty. It came back with the contents of the host's file printed right there in the body of the message. That was it. Proof of file read on the backend server through nothing more than a crafted name and a triggered password reset email. Let's pause for a second. If you had just found an SSTI vulnerability that lets you read any file the server has access to, what would you do next? Would you try reading etcd.passwd to fingerprint the environment? Look for SSH private keys, API tokens, or secrets sitting in user directories? Load internal config files, maybe grab database credentials or email service secrets? This isn't just a cool trick, this is a deep backend access, all through a single email template vulnerability. You are inside the server's brain just by injecting a string. So, how did this even happen? It all came down to one thing: trusting user input too much. The app took input from the user and passed it straight into the template engine. No escaping, no filtering. Then when the email system kicked in, it just rendered that input blindly while generating the message. And even though the engine was sandboxed, a function like source was still available, which means the attacker could start reading files from the server. Now let's talk about how this could have been prevented. Never feed raw user input directly into template engines. Always escape it or use a strict allow listing. In production, lock things down. Disable risky functions like source or anything that allows system access. And don't stop at testing the website. Check the stuff running in the background as well, like email templates, PDF exports, or anything else that quietly uses user data behind the scenes. Most teams test their main pages for injection. But what about the emails your app sends out every single day? That's where bugs like this hide. And for my fellow pentesters, here's how you can find vulnerabilities like this during your day-to-day testing. Don't just test the obvious stuff. Go beyond web pages, look at email templates, PDF exports, and any background features that quietly process user input. That's where SSTIs loves to hide. When you find a spot that looks like it's using a template engine, start simple. Try basic mass expressions. If you get a calculated response back, you have confirmed execution. Then move on to the fun part, which is real exploitation, and things outside the front end. R29K found this SSTI in a password reset email, not the site itself. So if you don't see reflection in the UI, don't stop. Try places like email content, logs, or even exports. And if you do get reflections, go further. See if you can read files from the server or call save system functions. Template engines were designed to make apps flexible and dynamic. But the moment user inputs get treated as code, trust me, the only limit is how far you are willing to push the boundaries. All of the vulnerabilities we covered today were responsibly disclosed, and that matters. Finding issues is only half the job. Helping teams fix them before attackers exploit them is what truly makes the internet safer for everyone. If you found this episode valuable, share it with 1 or 2 people who would appreciate it. Someone in your network might be building an API, writing a template, or skipping access check, and this episode could be the thing that saves them from making the same mistake. Let's make cybersecurity knowledge accessible to all. See you in the next episode.